Good morning. This is an experiment of measurement of losses in a given OFC. So here we are going to measure bending loss, propagation loss, and also we are going to measure the numerical aperture. So the initial setup for the measurement of OFC losses is we have a signal generator where we can generate either a sine wave or square wave, which has been given to an LED transmitter, which converts LED transmitter, which is having an electrical signal that will be connected to converted to light signal when we are connecting an OFC cable from LED transmitter to a photo transmitter detector. That is here again back the light signal is converted to electrical signal. Then once that signal has been converted to electrical signal, it has just been amplified just for the observation point of view. So next is a CRO for observing that signal. Whatever the electrical signal is converted to light signal, that we are going to observe it. So let me show the experimental setup. This is a function generator, or this is a signal generator which generates both sine wave and a square wave. So from the signal generator, it has been connected to an LED transmitter circuit, that is an emitter circuit, this connection. Next, I will be connecting a cable, OFC cable of 0.5 meter length. Next, that OFC cable is being given to that photo detector circuit, and the output of photo detector circuit is given to amplifier. This is an amplifier circuit, and from the amplifier I am going to observe in the CRO. These are the connections: signal generator, LED transmitter signal generator, LED transmitter circuit, OFC cable, then connection for the amplifier and observation. So when I connected 0.5 meter cable, I got some signal. So let me keep it for about 5 volt. Yes. Now I am getting a signal of about 5 volt amplitude using 0.5 meter cable. So let me take it as V1. For propagation loss, you need to measure what is the voltage that you are getting in a 0.5 meter cable and what is the voltage that you are getting in a 1 meter cable. So the voltage you are getting in 1 meter cable, you take it as V2, and then finally we can calculate the loss using the formula V1 by V2 is equal to e to the power minus alpha into L1 plus L2, where L1 and L2 are the length of the cable, that is 0.5 meter and 1 meter. So now I will be replacing the cable slowly. So freely connect it. Yes. So once the connection is over, Now you can see a small change in the voltage when it was 0.5 meter cable. We had got 5 volt and now it is around 4.6 volt. So V1 will be taken as V1 is taken as 5 volt and V2 is taken as 4.6 volt, and the calculation is done, and finally alpha will be calculated, and alpha is also called as attenuation loss, which is nothing but a propagation loss. So this is all about finding the propagation loss. Next, let us move to bending loss. For bending loss, we have to take the cable which is of longer in length. So let me take this 1 meter cable itself, and let me adjust this voltage for 5 volt. Initially, let me keep it as 5 volt using a signal generator. Yes, now I have set 5 volt initially without bending. So that I'll take it as X. X is nothing but the initial voltage, 5 volt without bending. Now let me bend and see what happens to the voltage. So for the first bend, there is a very small decrement in the voltage because it doesn't affect much, but still you can observe that it is around 4.8, correct? Yes, the voltage you can take it as Y, you can take it as 4.8 volt. Next, for other bending, you can again see a change. Which is of about 4.4 or 4.5. You can take it as 4.5. That is Y is taken as 4.5. So the loss is X minus Y, that is 5 minus 4.8 volt and 5 minus 4.5. So that is the loss. So preferably OFC cable is used in communication when it is straight. So if there is a bend in communication for long distance, there will be a loss. So OFC is almost used in short distance communication, especially in telephone industry. Next, I want to see what is the numerical aperture of an OFC cable. So numerical aperture means it is the ability of an OFC to measure how much light it is going to transmit. That is, aperture is a measurement of the emitting surface, how much light it is going to emit. So the setup is, you take a 1 meter cable or 0.5 meter cable, whatever it is, and connect it to a measurement jig. This is a device wherein you are going to measure the numerical aperture. It is having a wide screen of different concentric circles, that is of 10 meter, 15 meter, 20 meter and 25 meter. So here this is a length scale. So you can see a small red color light, that is nothing but OFC light. So now I am to measure to what extent it is going to be emitted, correct? So I'll place this white screen so that the light has to cover the different concentric circles for different length. So first I'll keep it at some distance, and now I am trying to keep the light so that it has to cover the first circle, 10 meter circle. So for some distance it is covering the first circle, 10 mm circle. So the distance is something around 0.9 centimeter. So this is in W. Width of the concentric circles is expressed in meter and the length is in centimeter. So convert it into meter. 0.9 centimeter, convert it into meter and take down the reading. So W is 10 meter and L is length, that is 0.9 centimeter, converted into meter. We have the formula for numerical aperture, that is equal to W divided by 4L square plus W square whole to the power 0.5. To the calculation so that you will get numerical aperture. But always numerical aperture is expressed in terms of angle because we are measuring the emitting surface or emitting light, which is always expressed in angle, especially in case of antennas or OFC, anything. So that value, numerical aperture is equal to sin theta. So theta is equal to sin inverse of numerical aperture. So this is how you can find out the numerical aperture of OFC. So this is all about the measurement of losses in a given OFC, that is bending loss, propagation loss and numerical aperture. Thank you.